Welcome back to another explainer. Today we're diving into the core math that makes modern biomanufacturing possible. We're going to take a structured whiteboard-style masterclass approach to really master the foundational mathematical models of bioreactor kinetics. Think about it. An industrial bioreactor isn't just a giant random vat of biological soup. No way. It is a highly controlled mathematical environment, meticulously designed to optimize cellular life. Whether we're looking at a small laboratory flask or a massive, multi-story industrial tank, we are using strict engineering principles to dictate exactly how these biological organisms behave. Here's our game plan for today. We'll start with the math of microbes, hit the monode growth model, scale up to continuous chemostat design, tackle biomass yield and substrate, and finish off by bringing it all together with a fully solved example. Okay, section 1, the math of microbes. Let's quickly review our bioreactor basics. When we're scaling up biological processes, bioreactors give us the physical tools to maintain the absolute perfect conditions for growth. We're talking about using cooling jackets, impellers, and spargers to tightly control environmental factors like temperature, pH, aeration, and agitation. The whole goal here is biotransformation. We feed a substrate or a nutrient to a cell so it can churn out a highly desirable product, things like life-saving penicillin or industrial citric acid. Moving right along to section 2, mono growth model kinetics. This is where we zoom in on the micro level. To really grasp how these cells grow in response to the environment we just built for them, we need to meet the key players in our mathematical story. First, we have mu, the specific growth rate of our cells. Then, mu max, which is the absolute peak growth rate under perfect conditions. Next up is S, the substrate concentration, which is essentially the limiting nutrient available. And finally, Ks, the Monon constant. This one is really important. It represents the exact substrate concentration when the growth rate hits exactly half of its maximum. Now, the absolute star of the show here is the specific growth rate, mu. The monode equation gives us a precise mathematical link between the food available to the cells, our substrate, S, and how fast they reproduce. As the substrate increases, the growth rate increases, right up until it hits that hard biological limit of mu max. This one simple equation literally dictates everything that happens inside the vessel. All right, part 3, continuous chemostat design. Let's look at the macro level. Let's see how our micro-level math scales up to the actual vessel. In bioprocess engineering, we typically compare batch and continuous cultures. A batch culture is basically a closed system. You add food once, the cells grow, the nutrients run out, and the culture eventually dies off. Pretty simple. But for industrial scale-up, engineers often use a continuous system, like a continuous stirred tank fermenter. This is an open system. You have a constant feed of fresh nutrients coming in, and your product is continuously being siphoned out. This keeps your microbial workers in a highly productive, non-stop state of growth. And this brings us to exactly how we mathematically control this continuous environment. We use a metric called the dilution rate, or simply D. The math here is incredibly straightforward. D equals F divided by V. F is the flow rate. Think of it as the faucet feeding fresh nutrients into the tank. And V is the working volume of that tank. This single number tells us exactly how fast the liquid inside our bioreactor is turning over. Which leads us straight into section 4, biomass yield and substrate. It's time to define our output. Now that we have a handle on the kinetics of cellular growth and the physical controls of the tank, we arrive at the most elegant, honestly almost magical part of steady-state chemostat design. In a continuous system that's running at a steady state, the specific growth rate of your microorganisms, mu, perfectly and automatically balances to match the dilution rate, D, that you set with your physical pumps. If you flush liquid through faster, the cells literally grow faster to keep up, assuming they have enough food. So mu equals D. Because our growth rate, mu, perfectly locks in to equal our dilution rate, D, we can use those monad variables we learned earlier to confidently calculate our outputs. We can find our effluent substrate, S, which is the unconsumed nutrient leaving the reactor. We can find our biomass yield, X, which is the total concentration of cells we successfully produced. And bridging those two together is the yield coefficient, which tells us exactly how much biomass is formed for every single unit of substrate consumed. And finally, section 5, a solved example. Let's bring all this theory together on the whiteboard. Let's put this into practice. Imagine we have a specific microbe with a max growth rate of 1.0 inverse hours and a monode constant of 0.2 grams per liter.
We put these microbes into a continuous reactor with a flow rate of 500 liters per hour and a working volume of 1,000 liters. The core question for an engineer is, what is the steady-state effluent substrate concentration? Or, simply put, how much food is left over in the fluid leaving our tank?
All right, let's break this down step by step. First up, we find our dilution rate, D. Flow over volume means 500 divided by 1,000, which gives us a dilution rate of 0.5. Second, we apply our golden rule of steady state. Mu equals D, so we know our cells are growing at a rate of 0.5. Third, we take that original Monod equation and we algebraically rearrange it to isolate our unknown S. Finally, step 4. We plug in our known values, so S equals 0.5 times 0.2, all divided by 1.0 minus 0.5. Do the math, and boom! We find that the steady-state effluent substrate concentration leaving our reactor is exactly 0.2 grams per liter. Notice how clean that is? By simply dictating the physical flow rate of our pumps, we can mathematically pinpoint exactly how much unconsumed food is escaping the system. And this right here reveals the true power of steady-state design. Finding your leftover substrate unlocks the rest of the entire system. Once you know S, you can use the yield coefficient to perfectly calculate your biomass yield, X. This is how bioprocess engineers optimize industrial production. They minimize wasted nutrients while maximizing the output of those incredibly valuable cells or products.
As our source material from Microbe Notes points out, a good bioreactor design directly helps to improve productivity and provides higher quality products at lower prices. Mastering these basic mathematical concepts, monode kinetics, dilution rates, and steady-state rules, is absolutely foundational for scaling up the bioprocesses that can quite literally change the world.
So I'm going to leave you with this final provocative thought to ponder. If we can use fundamental math to perfectly control the growth and biotransformation of microbes inside a giant steel tank, what humanity-saving products, from novel antibiotics to clean biofuels, will we engineer next? Keep learning, keep analyzing, and we'll see you in the next explainer.